So let's look at that last example from the last video again. This is actually a very special series called the harmonic series. Right? This one here. It's 1 plus 1/2 plus 1/3 plus 1/4, 1/5, and so on. Right? So that divergence test, we took the limit, it goes to 0, so the test doesn't tell us anything. Right? So let's look at what's going on here. Right? So here, let's look at the partial sums of this. Right here, this line right here gives us the partial sums. All right, so the sum of the first n terms. And what I've made here is a plot of this where I can manipulate the value of the number of terms we're adding up from 10 to 1,000. Let's go ahead and run that. Right? So if we look at this here, it's going up here. Looks like it's maybe following some kind of a square root or a logarithmic curve. If I remember this correctly, this should be somewhat logarithmic. All right. And as we go further and further, look what happens. So what do you think's going on here? Do you think this is going to level out and converge somewhere? Or do you think that this is going to go off to infinity? Right? Even from this picture, it's not perfectly obvious, right? It could potentially level out. Now I would say you would be wise to remember the graph of ln of x here, because ln of x also looks like it's going to level out, but it never actually does. So let's go ahead and try and figure this out analytically. So let's look at the nth partial sum, right? So each of these dots would represent, like, this is 1 plus 1/2, this is 1 plus 1/2 plus 1/3, and so on. So each one of these dots represent this sum right here. So one thing I want you to notice is that sum right there is exactly a left Riemann sum for the integral of 1 over x from 1 to n plus 1. Right? It's a Riemann sum with n rectangles and left endpoints. Right? In particular, here's an example for n equals 9. Right? We have our 9 rectangles here. Right? Here's our 9 rectangles. And this one has height 1. This one has height 1/2, 1/3, 1/4, 1/5, 1/6, and so on. Right? And notice if we plug in n equals 10, the area of each rectangle corresponds to each entry here. Right? So what does that tell us? Well, if we look carefully at this, let's see here. I feel like the graph is missing. I think the graph should be here, but I apparently messed something up. Open that back up. Oh, I guess it isn't there. Okay. Never mind. Let's close that back up. All right, so the graph of 1 over x would be here. It passes through all of these left endpoints here, though. So the interesting thing about this graph is it's an underestimate, or sorry, an overestimate of the integral. And so, since it's an overestimate of the integral, we know that this left Riemann sum here is greater than this integral. All right? For every value of n, no matter what I pick, each of these rectangles is always a slight overestimate of the area that's added on. So if we take the limit as n goes to infinity, well, this is true. Now, what's important about that is this is the harmonic series right here. This thing right here. This is the series we want to know something about. this is an integral that we can compute. Right? This is like everybody's first improper integral. So, I'll let you remember how to compute this on your own or just use Mathematica, but this integral turns out to diverge, right? This integral is infinite. So, since the series is greater than the integral, that's saying the series is greater than infinity, and so therefore, the series must also diverge. In fact, the series adds up to infinity. All right. So, that's a pretty interesting result, right? Something like this you would expect to add up and it, maybe get a finite number out of it. But this is an example of a series whose limit of the sum ends, limits of the individual AKs here, that limit is 0, but the series still diverges. So this is why it's really important to note for that divergence test that just because the limit is 0 does not mean that it converges. So this concept here that we did for the integral test, this actually does generalize a little bit. I really thought the function was here somewhere. This does generalize a bit. And this gives us something that we call the integral test. So what is the integral test? Well, what we do is, we look at our series, right? We have a sum of AK. We want to think of this AK. We want to change it into a function, right? So usually that just means, swap K for X. We did something like this when we were doing finding limits of sequences, right? We were thinking of this as a function of K and then just doing that limit. So the interesting thing here is the integral test tells us if all of these terms here are positive, right, and we can have a function f that equals each of these at the various k values, then if we integrate that function from 1 to infinity, if that converges, then the series must also converge. If that diverges, then the series must also diverge. So this infinite series and this improper integral are very closely tied to each other. Right? If one converges, so does the other. If one diverges, so does the other. Now, one very important thing here is this last line, that the value of the integral is not equal to the value of the series. Right? That's very important to keep in mind. If you can compute that integral, that doesn't tell you what the sum of the series is. Right? Just keep that in mind. So let's look at a couple examples to close this out here. So let's figure out whether the following series converge or diverge. Right? Example 1 here, let's look at the series k equals 1 to infinity of 1 over k plus 8 to the 3 halves. Right? So let's look at this. Right? This thing right here, if we were to apply the divergence test to it, the limit would equal 0. And so the test is inconclusive. So let's try our new fancy test, the integral test. Okay. So what that means is, well, this function right here, if I take f of x equals 1 over x plus 8 to the 3 halves, right? Each time I plug in 1, 2, 3, 4, so on, that's going to give me exactly the terms in this series here, which is great. That's exactly what we want. And all of these are positive numbers, so we're good to go. Right? It is very important that we use positive numbers for this. Otherwise, this comparison does fail. Right? In general, anyway. So we want to integrate this from 1 to infinity. Right? So we want to compute this. First things first, we can't really deal with this as it is, so we want to do a u substitution here. u equals x plus 8, and then du is simply dx. Right? So this is going to be 1 over u to the 3 halves du. Okay? And then the bounds, well, plug in 1 here, and we get 9. Plug in infinity here, or really take the limit as x goes to infinity. And, okay, well, infinity plus 8 is infinity again. Right? So to do this integral, remember, we have to swap the infinity for a limit. And here I'm going to swap this to u to the minus 3 halves, just so it's easier to look at. Right? Do this limit, or sorry, do this integral. So this is going to be negative 2 u to the minus 1 half, right, from 9 to b, which is limit as b goes to infinity of, this is negative 2 b to the minus 1 half, minus negative 2 times 9 to the minus 1 half. Right? Here, since this right here is a negative power of b, this is going to go to 0, which is great. Right? And that leaves us here with this, I'll let you work this out here, but this is just going to go to 2/3. Right? That's a finite number. So this integral converges. So integral converges, which implies that the series converges. Right? And that's that. Right? Again, we're not going to know what it actually converges to. The value of that integral doesn't tell us what the value of the series is, but what we for sure do know is that it has to converge. Okay, so let's look at another example. All right, and we actually had this example earlier. Let's look at the sum as k goes from 0 to infinity of k over k squared plus 1. Right, so again, a good function that'll work here is simply just replace the k's with x's. Okay. And I want to compute the integral of this. Okay, so integral from 1 to infinity, x over x squared plus 1 dx. So to compute this integral, first things first, we're going to have to pull off a u substitution on this. Take u to be x squared plus 1. du is going to be 2x dx. So here we're going to have like 1 over u, 1/2 du. And the bounds, well, plug 1 in here. The bottom is going to be 2. Plug infinity here. Top is going to be infinity again. Right? So do the usual thing. We can't actually plug in infinity, so we have to take the limit. 2 to b. This is going to be 1/2 over u du. I should have factored that 1/2 all the way out first, but we'll do it now. I'm just going to pull it all the way out. And we got limit as b goes to infinity. Here we have ln of b. Oh, sorry, ln of x from 2 to b. Right? So this is 1/2 limit as b goes to infinity of ln of b minus ln of 2. And if you remember, ln does go to infinity, albeit very slowly. So this limit is infinite. So here we have that the integral diverges, which implies that the series diverges. All right. So this is just, a couple examples of, in both cases here, the divergence test fails for us. It doesn't actually tell us whether we have convergence or not. However, we see that, in one case, in the first case here, the series converges. In the second case, the series diverges. Right? So just to sum this up in a nice way, there's a test that, a quick test that goes along with the integral test here. Let me pop back over to Mathematica. Right? There's something called the p-series, right? So last semester, I talked about this kind of general integral here, integral 1 over p dx from 1 to infinity. And we looked at different values of p and said, when does it converge? When does it diverge? Right? This integral converges as long as p is greater than 1. This integral diverges when p is less than or equal to 1. So from that, we get something called the p-series test. If we combine the convergence properties of this integral with the integral test, we get the so-called p-series test, which is this series here, the sum from 1 to infinity of 1 over k to the p. This series right here will converge as long as p is greater than 1. So even if it's like 1.00001, that's bigger than 1, so it must converge. On the other hand, if p is less than or equal to 1, then this series is going to diverge. Right? And we'll just look at a couple examples here real quick, just to point some stuff out. So this series here, this first one, if we look at this as a p-series, this is the sum of 1 over k cubed. So the p-value there is 3, so that series has to converge. If we look at the second one, the fourth root of k cubed, if we rewrite that as a single exponent, that's going to be 1 over k to the 3/4 power. 3/4 is less than 1, so that second series has to diverge by the p-series test. So that's a wrap up to this. I know it's a bit of stuff going on in this particular video here, but it's a pretty important test.